Welcome to Aviation Academy. I help you become top of your class without the fear of failure or wasting time. Because you deserve to perform at your highest level. My name is Tommy. I'm an airline pilot, flight instructor, and flight examiner. Now, let's hand the word over to our favorite examiner, John. Good morning, Tommy. Go ahead and explain the concept of VMCA for me. Certainly, John. VMCA, or Velocity Minimum Control in the Air, is a very important concept for us pilots to understand, because not understanding it and respecting it can quickly cause a loss of directional control, which can lead into an upset or a spin and a fatal crash. VMCA is defined as the minimum calibrated airspeed at which directional control can still be maintained after a sudden loss of the critical engine, and resume straight flight at the same speed using maximum 5 degrees of bank. VMCA is marked on most airspeed indicators with a red line and established by the manufacturer during testing. And it's very important to note that VMCA is not a static speed. It can vary greatly depending on flight control inputs, configuration, and environmental conditions. John, would you like me to go into more depth about the conditions they use to certify VMC? So for the certification of VMC, I have an acronym. This is the criteria they use to establish VMC. It's very similar to a just after takeoff situation, where it's still full power on both engines. We suddenly lose the critical engine and it's still windmilling. It's not being feathered. Gear has come up, flaps still in takeoff. Maximum 5 degrees of bank allowed into towards the operative engine. And you have to be able to regain the heading and assume straight flight within 20 degrees from the original heading. Okay, so can you explain to me what is a critical engine? Critical engine is the engine that would most negatively affect us if we were to lose it. On a conventional multi-engine airplane, the left engine is critical since the propellers rotate in a clockwise direction. That is due to factors such as P factor, accelerated slipstream, spiraling slipstream, and torque. Let me explain. So, first one up, P factor. When the airplane is flying at an angle of attack, the downgoing blade is going to have a bigger angle of attack than the upgoing blade into that relative width that is hitting the propeller. That causes the lift to be, or thrust in this case, to be unevenly distributed on the propeller, which will be something like this. We have the airplane, as seen from above. The lift will be shifted towards the right hand side of the propeller. As we know, force times arm equals moment. It's the same force on total force on both sides, on the left and the right. Let's assume we're having full takeoff power in this case. But due to the different arm, which will be longer on the right hand side, we're going to have a larger yawing moment from the right engine compared to the left engine. That makes the left engine the critical engine to lose in this case. Accelerated slipstream. Let's see, I'm going to write it up here. Accelerated slipstream can best be explained with the airplane seen from behind. When the airplane is flying along with the accelerated air coming from the engines, it will create more lift behind the propeller and around. And the lift being generated is slightly shifted towards the right-hand side due to P factor as well. And that makes the arm longer. If we were to put some numbers, it's maybe easier to imagine, but it's a longer distance from the center line of the airplane to the right-hand side highest lift vector compared to the left-hand side. That makes the left engine critical in this case. Next one up, so spiraling slipstream. When the propellers are rotating in one direction, it will create the slipstream that is rotating in a certain direction. That will cause the air flow to shift, and in a case of a multi-engine airplane, it will be something like this. So if I use this model airplane, if the right engine is failed, the airplane will yaw and roll to the right. Now this spiraling slipstream will hit the vertical stabilizer and assist in getting the nose back to its original state. The other case, if I lose the left engine, the yaw and the roll will be to the left, but this spiraling slipstream is not hitting the vertical stabilizer, and it will not assist the nose coming back to its original state. Therefore, the left engine is the critical engine due to this factor. Last one up, torque. Torque is when the propellers are rotating in one direction, clockwise in this case, it will generate an equal and opposite reaction. So the opposite reaction will be to the left in this case. If we were to lose the right engine, the plane will both yaw and roll to the right. However, now you can see the torque effect is assisting our directional control. It's working against the negative effect of the lost engine. When we lose the left engine, the plane wants to yaw and roll to the left, and the torque will assist that motion. That makes, again, the left engine the critical one to lose in a multi-engine airplane. So now we can see that P factor is mainly yaw. This is roll, yaw, and this is yaw and roll. So John, would you like me to expand on the factors affecting VMC? Yes, that was going to be my next question. Continue. So, factors affecting VMC. On one side, we have controllability. On the other side, we have performance. Controllability is connected to VMC. The more controllable the airplane is, the lower the VMC is. So let's look at the factors. Density altitude. So low density altitude has the same effect as having high power. High density altitude, the air gets thinner, fewer air molecules, and the engine operates at a low, similar to a low power setting. The explanation is pretty much the same. So if we imagine the airplane as seen from above, with the left engine inoperative, we will have asymmetrical thrust being generated from the right engine, and we need to apply rudder to oppose this yawing and rolling. Of course, we need to have the CG present, and it rotates around the CG. So sometimes when explaining this, I like to use the model airplane. imagine pulling strings. So this would be like pulling a string here, and the airplane turns around with CG. And here is also a string pulling the tail back to its original state. More power will equal more yawing. Less power is less yawing, and the need for less rudder to counteract that. The same thing happens when you fly at a higher density altitude. The generated thrust will be less, meaning that you have less rudder needed to counteract the yawing. Next one up is the CG position. So for the CG position, you can once again draw the airplane seen from above. Left engine is out, and the right engine is generating asymmetrical thrust. We have the CG in the forward position and CG in the aft position. So if we throw in force times arm equals moment, what we're going to look at in this case is the arm difference between the distance from the rudder to the CG in both a forward CG and an aft CG. We throw in some numbers here, 20 and 10. We can see the force is the same because that's the, in this case, maximum rudder input. We cannot press more rudder, it's maximum. Multiplied by the different arm will give a different moment. So a forward CG will make the rudder more effective so it can counteract the asymmetrical thrust being created. Forward CG will then be good for VMC, bad for performance. Critical engine, we have already discussed critical engine, but we're going to take a look at propeller condition. Windmilling versus feathered. So a windmilling prop will generate drag. We have once again the airplane as seen from above. Left engine is dead, and the right engine is generating forward thrust. Now, since this propeller is rotating and creating drag, it will be back to the string theory, pulling and pulling, and it rotates around the CG. So that's very negative effect for when it's windmilling, when you have asymmetrical thrust and it's pulling back on the inoperative side. What can we do? We can feather the prop and we get rid of a lot of drag here, which will make the airplane more controllable and make the VMC lower. Okay. Next one up is flap and gear. Flap and gear will create drag, which will benefit VMC when it's down. Let me explain. So the airplane, once again, seen from above. Left engine is dead, and right engine is generating thrust, and the airplane is turning around the CG. Let's add some flaps to it and gear. So when the flaps and gear is down, it will generate more drag on the operative side than on the inoperative side. That is due to the accelerated slipstream hitting the drag surfaces, the flap and the gear in this case, and creating more of a pull on the operative side compared to the inoperative side, which will benefit VMC. There's also another effect with the gear. Two other effects. That's the fin effect and the keel. So let's see. airplane, seen from behind, left engine is dead. And if I draw in the gear and some gear doors, when the airplane wants to yaw and roll to the left, like in this case, this is like having added vertical stabilizers. Makes the airplane wants to seek the nose into the relative wind and makes it more stable. The keel effect will be like shifting the CG slightly downwards, and like on a sailboat, the long keel underneath has a weight which makes the sailboat more stable. Shifting the weight downwards makes it more stable compared to having a CG higher up. So flaps and gear down is beneficial for VMC and worse for performance. Next would be bank and side slip. The last one is weight, and it's pretty much the same explanation for them together, so I'm going to combine them. So let's start off with imagining the relative wind here, okay? So if the relative wind is coming in this direction and we're flying along, we lose the left engine, and I would step on the right rudder to counteract this, only the rudder with wings level. I would be flying like this with the fuselage exposed to the wind, causing a lot of drag and unnecessary use of the rudder, which would make the rudder being closer to its limit. The other scenario is if I would use only aileron to counteract this left engine out. I would be flying with the side slip, in this case towards the operative engine, not in this direction, but towards the operative engine with bank. And I would be flying sideways, exposing large surfaces on the airplane, causing a lot of drag, a high angle of attack on the tail, which could eventually cause the tail to stall out, and the airplane would enter a spin. So what can I do? I can add some bank and rudder to fly zero side slip into the relative wind. With a multi-engine airplane, it's about 2 to 3 degrees of bank in towards the operative engine, and roughly half ball deflection towards the operative engine that causes us to fly zero side slip. There's really no instrument that indicates this, but we can add, for example, a string on the windshield, which is often called a yaw string, so we can see that we're flying with a zero side slip. Okay, so moving on to why this occurs. If we can visualize the airplane banking, again, the left engine is dead, and already the pilot is banking in towards the operative engine. The lift generated will be perpendicular to the wings, so something like this, and we have the weight acting down, and we have the vertical component here working against the weight. So what we have created now is a horizontal component of lift. So in this case, the airplane is flying in a straight line. Take note, it's not banking to the right, it's flying straight, but with bank added. So the horizontal component of lift is helping the rudder to become more effective. Bank would only be positive for VMC if we're banking in towards the operative engine. Now let's take the case of adding more weight. If I add more weight, I need to add more lift. Adding more lift will create more horizontal component of lift, making the rudder even more effective. So therefore, a heavier airplane banking in towards the operative engine will make the rudder more effective. So you could most likely get the same horizontal component of lift at less bank with a heavier airplane compared to more bank at a lighter airplane. So that takes care of the explanation for side slip and bank and the weight. Now, what we can do is we can make a table out of this and say that, like I said initially, I talked about controllability on one side and then performance on the other. If I write up controllability here and VMC, those are connected. Performance on the other. We could start taking a look at the conditions that they certify VMC in and start off with at the top again and say for the density, what's good for performance is dense air. So dense air. What's good for controllability and VMC would be less dense. For the power on the engines, causing the asymmetrical thrust, more power is good for performance. More power. In terms of controllability and VMC, obviously that would be the opposite. So low power. For the CG, that would be for performance aft CG. And for controllability, that would mean a forward CG. Critical engine and wind and propeller condition, that would be, in terms of performance, it will be feathered. And for the controllability and VMC, it's the non-critical engine, feathered. Flap and gear for performance, up. And flap and gear for controllability and VMC is down. For bank and side slip, in terms of performance, we want to fly at 2 to 3 degrees into operative. At 0 side slip. For the controllability and VMC, more bank would be beneficial for VMC. And in terms of weight, performance-wise, obviously that would be a light airplane. And for controllability and VMC, that would be a heavy airplane. And take note, that's only when banking in towards the operative engine. So to wrap this up, we can see that when they do the testing for VMC, most of these items actually makes the VMC increase and it favors performance. That's very important to know for a pilot, because when you're flying at different configurations and in different environmental conditions, you have this thorough understanding of how VMC factors affect the established and marked VMC speed on the airspeed indicator. If you enjoyed this video and you would like to see more, please like and subscribe.